So 13.7 part 2.
Did I show you? I don't know. What if I showed you? Why not you start out as
All right, so quick review of major concepts. So if we have Z, Z equals f of x, y. Let's see, del f is normal to level curves.
Really, it doesn't matter. It says it's 2 by 3.
Del f points in the direction of maximum rate of change. And I should, let me write up here, del f is a vector in the plane. So when we have z equals f of x, y, all of these things are true. Del f points in the direction of maximum rate of change, and our directional derivative in the direction of u is del f dot u, and we want u magnitude to be 1. So that was our first application of the gradient of del f. If we have f of x, y, z, what we talked about yesterday, f of x, y, z equals a constant, then del f is a vector in space. Del f is normal to the surface. And because it's normal to the surface, that also means it's normal to any tangent vector at a particular point. Normal to tangent vectors, and it's normal to our tangent plane. And at a particular point, at P0, x0, y0, z0, the equation of our tangent plane, get a nice equation, is f sub x, x minus x0, plus f sub y, y minus y0 plus f sub z, z minus z0, and that equals 0. So that gives us our equation of our tangent plane. So kind of the big picture things that we did with our gradient to our surface. So those are for the last couple of sessions. These are the big ideas that we've talked about. So what I want to do today is just go through some examples of some different types of problems that we can solve with the gradient as a normal vector to a surface. But I want to talk about these big picture things first. Is everybody good with all of this information? The gradient, like I said, when we first started, just when was that, last Thursday? When we first started talking about the gradient is a really important idea, kind of central to what we'll do in chapter 15, and we'll use a gradient quite a bit for the rest of chapter 13 as well. So it's a big, one of the big ideas in vector calculus is the gradient. All right, so let's look at a couple of examples. I love this next problem. So we have the surfaces. X squared plus y squared equals z, and z equals 4 minus y. We want symmetric equations of the tangent line to the curve of intersection at this particular point, at 2, -1, 5. So we need to figure out the symmetric equations for the tangent line to the curve of intersection of these surfaces. So first off, what are these surfaces? What is z equals x squared plus y squared? It's going to be a paraboloid. In the xz plane we have parabolas, yz plane we have parabolas. Parallel to the xy plane we have circles, so we get a paraboloid about the z-axis. How about z equals 4 minus y? The plane, right? So we have this intersection of a plane and the paraboloid. And we need to find equations for the line of intersection. So let's take a look at a picture here. There we go. There's our paraboloid and there's our plane. And the curve of intersection is that kind of elliptical shape. And we're looking for the symmetric equations for the tangent line to that curve of intersection at that particular point. So how are we going to go about this? What can we do? Well, what do we know how to find with the what tools do we have? What can we do with these surfaces? What's our go-to thing in the last few sections? Gradient. The gradient. What does a gradient give us? The gradient is going to give us a normal vector. So to find our normal vector, what do we need to do to these surfaces first? How do we have to express them? What do we need to do? So we need f of x, y, z equals 0. So I'm going to say f, let's say f is x squared plus y squared minus z. And g is 4 minus y minus z. So f equals 0 and g equals 0. We can find the gradient. That gives us normal vectors to each of these surfaces. So we'll find the gradient of each of these. So we get 2xi plus 2yj minus k, and del g is minus j minus k. All right, so here's what we have. We have this curve of intersection. So let's say this is a piece of the curve. There's the curve of intersection. And here's our point. So at this point we have these two normal vectors. I don't know exactly what they look like. We'll just draw them. So here's one. Oops. Drew it the wrong way. I picked my arrow going the wrong way. I wanted this arrow. There we go. So there's one, and there's the other normal vector. So this is, we're going to say this is del f, and this is del g. At this particular point. and we want the equation of the tangent line. I want to get my blue back here. So we want the equation of this tangent line. So there's my tangent line. What happened to my black? So we have these two normal vectors to our surfaces. I don't have the surfaces drawn in here. And we want the equation of this tangent line. So we know that the normal vector is orthogonal to the tangent line. Each of these normal vectors is orthogonal to the tangent line. For our symmetric equations for our tangent line, we need a point on the line, which we have here. What else do we need? A vector in the direction of the line. So given this information, how are we going to find a vector in the direction of the line? The cross product. If we take the cross product of the two normal vectors, they're each orthogonal to the tangent vector. So we need a vector that is orthogonal to each of these two vectors. Well, the vector that's orthogonal to two vectors is the cross product. So the cross product is going to give us our direction vector. So isn't this a nice problem? We have surfaces, we have gradients, we have cross products. It's like a mathematical poem to the glory of the Tranya. all these vectors, all this vector stuff going on. What's that? Textual evidence. So we have all of this nice vector stuff going on. So we're going to take the cross product of our gradient vectors, of our normal vectors at this particular point. All right, so del f at our points, del f at 2, -1, 5 is going to be 4i minus 2j minus k. And del g at our point 5 is minus j minus k. So we're going to form our cross product. Del f dot del g, or sorry, not dot, but cross del g. So we get our, oh, this looks familiar. Okay. Our normal vector. ijk. It does bother me that there's no vector symbols on the shirt, though. 4 minus 2 minus 1, 0 minus 1 minus 1. So I'm going to form that cross product. When I work this out, I get I plus 4j minus 4k. Right, it's in bold, right? So I got the answer right, at least. So these give us this gives us our direction numbers for our line. This vector gives us our direction numbers. This is a vector in the direction of the line. So our direction number is a equals 1, b equals 4, and c equals -4. So now I can write my equations for my line. So our equations for the line are, let's see, our point, let me get my point, x minus 2 over 1 equals y plus 1 over 4, and that equals z minus 5. I'm going to put that negative over 4. And those are my equations for my line. So that's the symmetric equations for the tangent line of the curve of intersection. kind of nice problem. Gradients, cross products, normal vectors. Questions there? Now, before going to the next problem, let's think about how we would have had to attack this, or the approach that we would have taken in chapter 12. So what could we, in chapter 12 we did some problems like this, where we found the equation, when we talked about vector valued functions, we found a vector valued function for curves of intersection. So what would we have had to do if we wanted to try to approach the problem that way? We'd have to parameterize our curves and find z in terms of x and y, something like that. Parameterizing a paraboloid, kind of difficult. Parabolizing or parameterizing a cylinder, not too bad because x squared plus y squared is a constant, so that's not too bad. But here our circle gets bigger. So parameterizing these equations, writing vector valued functions for that curve of intersection, kind of difficult. And then we'd find r prime. R prime would be in the direction of the tangent line at that particular point, and then that would have been kind of a complicated problem. But with our gradient, turns into not a bad problem. All right, another thing that our gradient as a normal vector lets us talk about is what we call the angle of inclination. So angle of inclination is a way of talking about how slanted a plane is. So if we have vectors A and B, say recall, mathematicians love to say recall, angle between A and B is given by, we can say the cosine of theta is A dot B over the magnitude of A times the magnitude of B. And we're going to define the angle of inclination of a plane . So we want our angle. So we have theta, angle theta, where 0 is less than or equal to theta, less than or equal to pi over 2. Between the plane we're interested in and the xy plane. And also recall that we said that we defined the angle between two planes as the angle between their normal vectors. So what we're looking at here is the angle between their normal vectors. We talked about the angle between planes as the angle between their normal vectors. What's a normal vector to the xy plane? Z or k hat. So k hat is normal to the xy plane. So our angle of inclination so cosine theta is going to be, and we're going to say the absolute value of n dot k hat over, and what's the magnitude of k hat? 1. So we can just say over the magnitude of n. And n is the normal vector to our plane. And we took the absolute value of the dot product to keep our angle between 0 and pi over 2. So this is how we find the angle of inclination of a plane. Take the dot product of our normal vector with k hat divided by the magnitude of our normal vector. And it tells us how slanted our tangent plane is. Why would this kind of thinking forward, think about what we do with where we're going to go with derivatives and that kind of thing. Why would it be interesting or valuable to know the angle of inclination of the tangent plane? So if we're talking about derivatives, what do you think our natural next step is going to be with these surfaces? What do we do with derivatives? Other than find rates of change. What's that? And we'll end up integrating them. But what's one of our major applications of derivatives? Maximums and minimums. Where do you think? What do you think is going to happen at the maximum or minimum of surface? What do you think is going to happen to the tangent plane? It's going to be parallel to the xy plane. So the angle of inclination would be 0. So our tangent planes are going to be parallel to the xy planes at maximums and minimums. So that's one reason it would be useful to know this angle of inclination. All right, so let's do an example, a couple of examples using this angle of inclination, looking at that idea of tangent planes and maximums and minimums. So questions on the idea here? Okay.
Oh, no.
So we have the surface, 2xy minus z cubed equals 0. So we want the angle of inclination of the tangent plane, and this is why we invented 2 years ago, we invented the symbol for tangent plane, because we end up writing the words tangent plane a lot. Of the tangent plane at the point 2, 2, 2. So we have the f of x, y, z equals a constant, 2xy minus z cubed. The normal vector to our tangent plane we find by doing what? Finding the gradient. So del f gives our normal vector. So del f, calculate our gradient, del f is 2y I hat plus 2x j hat minus 3 z squared k hat. And then at our points, evaluate that at a point, del f at 2, 2, 2. We end up with 4i plus 4j minus 12k. So that's our normal vector. So our cosine of our angle, cosine of our angle of inclination is the absolute value, just to rewrite this, n dot k hat over the magnitude of n. So n dot k hat is negative 12. Take the dot product, all I end up with is the z component, and the magnitude of n, square root of 16 plus 16 plus 144. I get the square root of 176. And if I simplify that, that turns into 4 square root of 11. So cosine theta is 12 over 4 square root 11, or 3 over the square root of 11. And if I plug that in my calculator, I get theta is approximately, find the inverse. What's that? We take the absolute value, because we want our angle to be between 0 and pi over 2. So our dot product was negative, but we take the absolute value. So if we plug that in our calculator, inverse cosine, we get about 25.24 degrees. Equals 1. Because k hat is a unit vector. K hat is a standard unit, so it's a unit vector in the z direction. Okay. So let's look at a picture. There we go. There's our surface. I graphed it from 0 to 5, and our tangent plane right there. And our point there, 2, 2, 2 is kind of right in the middle of that, box. So there's our surface, there's our tangent plane, and if I get it perfectly sideways here, let me turn it around this way. Measure that with a protractor. I was going to say, if we look at the angle between this and that, it looks like it could be about 25 degrees. All right, questions there? All right, so our last example kind of foreshadows what we're going to do for the next few sections when we talk about maximum and minimum, maximizing and minimizing multivariable functions. All right, guys, let's stay focused for just a little while longer. So we have z equals 3x squared plus 2y squared minus 3x plus 4y minus 5. We want to find where is the tangent plane horizontal. So where is it parallel to the xy plane? First off, let's see if we can figure out what the surface would be. Z equals 3x squared plus 2y squared minus 3x plus 4y minus 5. So our z term is linear, and our x and y terms are a shifted paraboloid. Very nice. So what we could do to figure that out is group the x terms, complete the square on the x terms, group the y terms, complete the square on the y terms to figure out our shift, our center for our paraboloid. So this would be a shifted paraboloid. So where do we think our tangent plane is going to be horizontal on a paraboloid? At the minimum or at the vertex. So at the vertex of our paraboloid. All right. So how are we going to figure out where the tangent plane is horizontal? How are we going to analyze that? We could find where theta equals or 0. So Will says let's find del f. So the del f is going to give us our normal vector. So if our normal vector and the k hat vector are related, how? Parallel. If our if our normal vector and the k-hat vector are parallel, then our tangent plane is going to be horizontal. So we want del f parallel to k-hat. So that we're going to figure out where del f is parallel to k-hat. So I'm going to find f. F is, I'm going to subtract z from both sides to get my f of x, y, z. So I'm going to say f is 3x squared plus 2y squared minus 3x plus 4y minus z minus 5. So there's my f of x, y, z, and that equals 0. So del f, our normal vector to our surface, is 6x minus 3 I hat from these two terms, and we get plus 4y plus 4 j hat minus k hat. And we want this to be parallel to k hat. So when is this, how are we going to make this vector parallel to k hat? What are our I and j components of this vector going to have to be?
0.
0. For this to be parallel to k hat, we need 6x minus 3 equals 0 and 4y minus 4 equals 0. And remember, think back when we talked about partial derivatives. We said that we kind of had the idea that our surface is going to be at a maximum or a minimum when the f dx and the partial with respect to y equals 0 at the same time, simultaneously.
4y plus 4.
Did I miss a sign here? 4y, yes, that should be plus 4. So our partial derivative with respect to x and our partial derivative with respect to y are 0 simultaneously. Well, this is a nice problem because we don't have to solve simultaneous equations. It comes out easily. We get x equals 1/2 and y equals -1. And when I plug that back in here to get our z components, or our z coordinates, plug x and y back into this, I get z equals -31 fourths. So if we completed the square here and found the vertex of our paraboloid, it should be at 1/2, -1, and -31 fourths. So we found where our normal vector was parallel to the k-hat vector. That should give us where our tangent plane is horizontal. So let's take a look at a picture of this one. There's our paraboloid. There's our horizontal tangent plane. I graphed our horizontal tangent plane. And right there at the vertex. And if we look at the coordinates of our vertex, where do we end up? Our shifted paraboloid, we're shifted just a little bit from 0, 0, 0. So there's our picture. Right at the minimum of that paraboloid. Our tangent plane is horizontal. And we also talked about this when we talked about the gradient. Right at the minimum, our surface in a very small area around that vertex is essentially flat. So our tangent plane is an approximation of the surface right there. Okay, I like these pictures. Oh, and our paraboloid is a little bit elliptical because we have a 3 on the x and a 2 on the y. Okay. Questions? All right. The gradient, when I learned about the gradient in calculus, in Calc 3, the gradient's such a cool thing. Such a nice tool. Homework. All right, there we go.